In just a moment, Brian Neufeld, PhD, Senior Scientist from EMA, is going to begin his presentation. So now I'm going to turn it over to Brian.
Hi, thank you for everyone for joining today. And we're going to have a demonstration on some advanced CAE tools for space charging. Before we begin the demonstration, what we'll do is we'll have a few introductory slides which will help set the background. And you can submit questions via chat during the webinar, and there will also be a form at the end of the webinar where you can submit questions that maybe you either didn't have a chance to submit or you wanted to have answered in a more detailed way. And our email addresses for Tim and I are shown on the slide. Okay, so we'll begin by trying to give a quick definition of surface charging. So we're referring to electric charge accumulation on the surface of space vehicles that spend time in a space plasma environment. So we're thinking of space charging when we speak of surface charging here. Now, surface charging can be a critical safety issue for space vehicles, and that's one of the primary motivations for why one would want to study it or develop tools to help study it. When we speak of surface charging, we'll consider the possibility of differential charging that may build up between adjacent surfaces or between the dielectrics and the vehicle ground. The figure here attempts to illustrate graphically what we mean by differential charging, and what we'll be reporting on later when we show some demos. We'll show some results on differential charging, and this will refer to adjacent materials, such as shown by the red arrow in the figure, that may develop a voltage between them and may present an opportunity for some kind of arcing or discharging. This type of discharge, the differential discharge, can result in damage to the vehicle surface or dangerous coupling of transients to internal electronics. And we may also refer to absolute charging, where a voltage develops between the vehicle and the plasma. Although this tends to be a secondary concern, it still can result in coupling of energy to antennas and may still need to be understood in a design program. Okay, so now that we've defined the background, we will attempt to express a little bit of how the tools we're demonstrating today may fit in to the bigger picture. And we believe that a complete surface charging analysis effort involves several tools or several components, and we're focused on this webinar of elaborating the tools we have developed to support this type of program. And all of our tools are complementary to the NASCAP-2K space charging software. Probably many of you on the line are familiar with this software. It's a great physics solver for space charging problems, particularly surface charging type problems. And we don't have anything. We don't think there's anything wrong with that physics solver at all. In fact, we like it very much, and our tools are simply some areas that we think are some areas where there might be ripe for improvement in a space charging program that uses NASCAP-2K. So our tools are complementary and address these issues that we believe are ready for improvement, and in the next slide we're going to try and illustrate that with a matrix, and then we also have a demonstration coming after that. So what we show here is a matrix and a flow chart that illustrate what we consider the kind of the primary components of a space charging analysis, surface charging analysis program. Now what you can see, if you start with the flow chart on the right, you can see this natural flow from geometry through materials and mesh, through the actual physics simulation, through to the results processing. And in the little blue subheadings, we've tried to highlight kind of where our tools fit in to this big scheme of it. So the matrix is complementary to the flow chart. So the matrix shows, if you start with the geometry idea, well, two of the important pieces of that are native CAD import and advanced geometry development tools. And we've developed tools that facilitate both of these, both the native CAD and the advanced geometry, and they serve as a basis for creating a simulation object for spacecraft charging. Then you go down to the materials and the mesh. And our tools, as we'll show in a bit, allow the user advanced control of the mesh. You can control it. You can literally change the meshing algorithm with a couple of clicks of a button and generate a new simulation object with a different meshing algorithm. And within a couple of minutes, you can have that. And we'll show this in our demo. And also the material assignment is particularly important when you're importing something into the NASCAP environment. We can assign the materials. The user can define them by region within the EMA 3D platform, and they don't have to do element by element assignment. This can become important when you have, for instance, for one thing, you have to, even the first time you do it, it might take a long time. It might take a couple hours to assign them all if you have to do it element by element. But then every time you have to go back and update your model, then you don't have to go back and reassign materials. So that can be a real time saver. In terms of the space charging solver, we certainly defer to NASCAP-2K and think it provides a very reliable and strong environment for the simulation. Lastly, for the post-processing, certainly NASCAP-2K offers some post-processing. We believe it tends to be a manual process to use the NASCAP-2K processing. You have to maybe look element by element within the model to see the voltages that are developing. We've developed some automated tools that extract results based on material, breaking it down material by quantities, and we'll show that later. And we've also developed a 3D animation of the charging simulation, so that is something that you can't get directly from NASCAP-2K. So we believe that the 3D animation has value for developing some intuition. We'll show that in a bit, that sometimes it's a little surprising what can come out. And also, if you have to, maybe you have a presentation you want to give, or you need to show a manager some results, sometimes having this extra graphical tool can demonstrate that there's some real simulation going on and helps the user quickly get a feel for what you're doing. And then lastly, talking about these discharges that may occur, the EMA 3D framework allows the user to couple the geometry and the discharges into our electromagnetic solver and look at the transients that develop on electronics. Okay, so now we're going to move to the demonstration. So I'm going to talk through this demonstration. I've pre-recorded the video just to be efficient and not waste anyone's time. So I will talk through now this demonstration of a surface charging problem from the import all the way through the analysis. And it'll only take about 15 minutes. So the first thing we'll do is open up our model. And as I mentioned, our platform allows the user to open up and import a large number of different native CAD options. Our model is already in the Cadfix format, so we don't have to import it from a native CAD, but you could. And there's also these automatic repair and defeature options and wizards that can take you through importing a model and then making it something usable, so you have a faithful representation of the real vehicle. Now here's our simple vehicle for this analysis. We've already imported it, and we have made it watertight, which basically means it has a continuous surface. So all the surfaces are smoothly connected, basically. And once you've got the model imported and watertight, then you've done the hard work. So you have something you're ready to work with. Now what we'll typically do is divide the model into regions that correspond to the different materials. And so for instance, here I'll select some surfaces that I want to be my solar panels for this model. And once I select them, so it was that easy to select them, I just will add them to a set. So in the command line down there, I made a set called solar, and I plotted it. So the blue magenta here, or the purplish looking, is now my solar panels. For this simple model, we're just going to have 4 materials. And I've already selected the other materials, and I'll plot them now so that you can see how we've divided them. But it's the same process you just saw. So here's our limstat paint in the cyan color. Now we'll have our felt reusable surface insulation in red. That's a non-conductive thermal type material. And then we'll have a window in yellow. So that's going to be our model. We have we've got our geometry imported, and now we've divided the model up into regions based on what we want, how we want to assign our materials. So now we have a toolbox here, the NASCAP toolbox, and the first one, the first button on the right, allows us to define the materials for the model. So the user will see that you have a name, and then all of the different space charging materials associated with a NASCAP surface charging simulation, including the conductivities, the electron emission parameters, dielectric thickness, etc. So the whole gamut there. And the user just fills it out and hits OK. Now I've already defined my materials here for the sake of time. But now I just need to assign them to the different regions. So you can see the 4 materials are present. And for instance, we'll assign the limstat to the region, a limb, that's our paint region. Then we'll assign the frizzy to this region. Then a few silica for the windows, or for the single window. And then the solar panels will have their material as well. And so now we have a geometry that's been parsed by regions and assigned materials to those regions. So you have an import, a defeature, and then an assignment by region of materials. And now we're ready to make our NASCAP simulation object. And this third button here, you just define the set that has all the surfaces of your object, and then set a destination file name, and lastly you control the resolution of the mesh. The smaller number here gives you a finer resolution. And so once you select all of that, there's your mesh for the model. It's just come up, and I'm going to remove the surface plot so you can just see the mesh. And so here's your TR3 triangular type mesh for the model, and it's ready to go. And it's exported a file, actually, which we'll open in a minute, which is the NASCAP simulation object. Now, I'll point out that you can also do an advanced meshing option here, where you define the mesh yourself instead of using our built-in mesh algorithm. And it's the same thing. You assign the set that has all the surfaces and your destination file, but then you have some options within our mesh manager tool here to do your own type of mesh. And actually, after we finish this part of the demo, I'll show explicitly how you can do that very quickly and compare two different objects against each other. So now let's open the object we just made. So I'm going to open the NASCAP Object Toolkit, and we just exported this file.xml. So we'll open it up, and first we'll see is that the materials we assigned are present here. So the four materials, the Alimstat solar panels, a window, and Frizzy. And you can see those different sections are represented here on the vehicle. And one of the nice things is the materials, since they're already assigned, you don't have to go in and assign them element by element. You can see how tedious that process might be here if you had to go in and select all your elements to assign materials to. Here in the EMA 3D format, we do it just region by region, so it's much quicker that way. And then you can also modify your geometry and re-export it very quickly, and you don't have to feel the pressure of, well, I don't want to go back and have to assign all my materials again every time I need to change the size of a window or add an antenna or something like that. Now for this model, we've done a simulation in NASCAP-2K. I'm not going to show that just for the sake of time, but we ran this model in a geosynchronous plasma environment, in a shaded environment, and we're going to use the EMA 3D processing tools to look at the results. So this fourth button allows you to process any number of results based on the same object. So for this object we just exported, perhaps you had different illuminations or different environments you wanted to run it in. You can process as many as you want at the same time for the same object. Here we only have one because we only ran it for the case of geosynchronous plasma in a shaded environment. And then you pick the output name for the file, and then you have to go in and select the object file you used for the simulation. So I'm going to select the object I used. And then you need to select the results database, which is the NDB file that NASCAP produces. This has a lot of information on element by element results. And so we open up that database and extract the results element by element and material by material so that we can kind of break it down with a little more specificity. Okay, so now let's open, we just created a file that has a bunch of results that we'll look at. So you can see what comes out in this results processing is that you have all of the materials are represented, the four materials of the model, and then we have other columns that represent different physical quantities associated. So we talked about the differential voltage before. That shows the voltage between materials, worst case voltage between different materials. And so here the Alimstat and the Frizzy material have a large differential voltage with respect to each other. B conductor is the voltage with respect to vehicle ground. There's E-field normals on the surface. And then the last one is the voltage to plasma on each of the materials. So again, this will be the worst case and its absolute value here. So it's the worst case on that material. Now the environment column, so you see there's four environment columns. This would tell you if you had multiple scenarios that you were looking at, which of the scenarios produce the worst case for that material. Since we only have one here, there's only one. That's why the number one appears in every case. for this particular processing. Now, it's a pretty interesting result already. We see some large differential charging with the alemstat and the frizzy. We see some differential charging there as well with the solar panel, about 850 volts there. So it's pretty interesting, but maybe we can get a little more insight by looking graphically at what's going on. So this is where our animation processing comes in. It's the last button on the toolbar. So the user can go into this tool, and again, you define the set name that had all your surfaces, so the same one we used to create the mesh. And then you pick the number of time steps in your simulation. So we had 200 in this. Again, you go in and select your object file. And this time we'll select the NTM file that NASCAP produces, which has time series data available. What's going to happen is that the program is going to open up the object file and open up the NTM file and produce a database for Cadfix called an FRM file that contains the results information that will be loaded into this model once we've created it. So first we do the processing, and then we'll close out this model and reopen it, and it's going to load in this database that's just been created based on the results. So you see this FRM file here, which we just made based off of this model. So now we'll close it out and reopen it. And when we reopen it, it's going to read these results in, and then we'll look at the animation. Now the animation, we believe, can provide the user some interesting insight into the charging process that it's hard to see when you just look at the final time step. So we click on this particular toolbar, and you can see it has scanned in the results. So there's 200 time steps now. And the first thing we'll do is, so we're going to plot the potential with respect to plasma on all of the surface elements. This is at the final time step of our simulation. So you can see in the blue there, that's the frizzy, and the yellow is the alemstat. You can see that large charging differential there. And then the solar panels are visible as well. And they are actually charged less negatively than the rest of the vehicle. And you can see sort of a gradient developing between the solar panels and the rest of the vehicle, wanting to go from a more neutral charging to more negative. So this vehicle charges negatively with respect to the plasma. Now we can get a little more insight by actually doing the animation. And so that's what we'll do here. We can modify our graphics options as we want. There's a lot of different options for the graphics and how you plot. You can have a fixed scale, logarithmic, all kinds of options. And then in the animation option, you select the number of time steps, so we'll do every 4, and then we'll capture it. And this is showing the charging process from beginning to end, and it's creating an animation from it. And you can see some interesting things there. For one, initially the window charges up more negatively than the rest of the vehicle, but then as the charging continues along, the solar panels, which charge more neutrally, tend to want to offset some of that negative charging as they interact with the alemstat. And so the vehicle develops this compromise between the solar panels and the alemstat largely. But then the frizzy, because it has such a low conductivity, it's a very non-conductive material, it doesn't really join in the process very well. It doesn't respond that well to the solar panels, and so it stays negatively charged and develops that large differential charging. If the solar panels weren't there, the frizzy and the alemstat would probably have a much lower differential. They tend to both charge a bit negatively in the plasma, but because the solar panels are there, it creates this interesting dynamic. And so you can see that as you hit the animation. And you can change the speed at which this animation plays, and then you can save it as well, and that's what we'll do here. So you can save it pretty quickly. the animation you just created. You can also rotate the vehicle around and create animations in different angles. You can do several different animations looking at different parts of the vehicle. And so if we open it up, this is the animation we just made, and it's ready to go. You can, as I said, you can change the angles, you can change some of the settings on the graphics, and you can copy that right into your PowerPoint or just email it to somebody, whatever you need to do with it. And that's basically the process here from beginning to end. Now, I want to show one more quick demonstration.
Brian, before you move on, we have a question on whether or not you can access the individual cell results.
So meaning like element by element results?
Correct.
You can certainly do that. Now, we don't have this set up right now within our processing to give you element by element. But we do have, for instance, the animation, it gives you the min and the max and the full color scales, and we've broken it down by material, but it wouldn't take too much to get it cell by cell if the user needed it like that.
And then one more question, which I think I can answer. There was confusion on the changing peak in the color scale, and I'll just point out that in that results manager you can set so that the color is based on the peak at each time step, or it can be a constant scale across all time steps. So that's an option to the user. And I think that catches us up on questions.
Okay, thank you, Tim. We'll show one more quick demonstration here. So going back to the point that I made earlier about the mesh, I want to show you, so this was the model we just created in Mesh. And now in this demo, I want to show you quickly how you can easily change the mesh of the model and create a new simulation object, and you can compare different objects against each other. So I delete the mesh here, and I select the set we've been working with. SALL has all the surfaces. And I go into this mesh manager, and I'm going to change the mesh algorithm to a curvature sensitive meshing. And I can change the resolution. I picked 5 here just because it ended up looking the most natural to me. And I remesh and repaint it, and boom, here we have the same object, same geometry with the materials, but we have a different mesh. This mesh focuses a little more on maintaining the curvatures of your geometry, and we'll see that when we look at we compare side by side this mesh with the other one. So now we use the advanced tool. Again, we'll just pick this set, SALL has all the surfaces, and I'll change the name here, file 1. And so that quickly we've created a different simulation object with a different meshing algorithm. Now we can look at these side by side and see a little bit of the difference. And you might have a problem where you're really focused on maintaining the curvature of your geometry when you go to the mesh. This mesh that we just did might be better for that. And the original mesh, which is shown now on the left, might be a little better for maintaining a smoother mesh. And so when we look at them side by side, you'll see the different qualities of them. But you can see how fast it is to go ahead and create. You could create 4 or 5 of these and explore the different, see the sensitivity of results to several different meshes and see the numerical stability and things just with a few minutes. This is all in real time, so there's nothing hidden about the time scale here. And so literally this whole thing is about a 3-minute demo, and we've got 2 meshes ready to simulate. You can definitely see, though, the difference. The one on the right maintained the shape of that window especially much better than the one on the left. But the one on the left is nice because it's maintained a bit of a smoother mesh. If you look carefully at this window, you can see because you maintain that curvature so well, you get some pretty small elements in there. So that can, depending on what you're doing, that may be an issue. The one on the left there, again, has lost some of that curvature. but it's a pretty smooth mesh all the way through. So this is just an example of how you can easily create different meshing algorithms for your object. The materials still import through. They're still ready to go. You can just hit simulate on them, and they're ready to go. And you can do that for the different meshing algorithms, and you have control over that as the user. You can go in and play around with the parameters in the EMA 3D side and look at the different options available and decide on the type of resolution you want, things like that. Okay, so I'm going to go back now to the slides. That's the end of the demonstration part. And I'll just give a couple summary slides here which have hopefully encapsulated what we've shown today. We've provided what we believe is an efficient and powerful way to get realistic geometry from native CAD into NASCAP for a surface charging program. This includes the material assignment. You can easily update geometry and have a ready-made simulation object, and then you can, as we showed, control this mesh properties. We have some post-processing capabilities which we believe enhance a little bit what's available with the NASCAP-2K. We've shown the material by material breakdown. Someone asked about the element by element. We could add that feature if someone wanted it. But as it is right now, we have the different quantities broken down by materials over the worst case. And as we showed, we have the full 3D animation. Sometimes this can provide a nice intuition, and it can also just be a nice graphic for talking to the people communicating your results. And as Tim said, you have the scale that changes. You can fix that to be a constant scale if you want. You have different ways of even showing the results in terms of the colors and the way that the model is illustrated graphically. Okay, so now it's the end of the content, the technical content of this, and just remind you we have our emails here. You can submit the questions. I'd like to also remind you that we do a webinar like this about every few weeks, and if you go to our website and submit your email, we can keep you on the list for upcoming webinars. We're also open to the suggestions for webinars. We do a whole host of different E3 topics outside of just space physics things. And this webinar is going to be posted online, so if you want to go back and look at it again, if there was something you missed or wanted to check, then you can go online probably later today or tomorrow and get it. And there's also going to be a form here at the end of the webinar, so maybe you don't want to submit a question right now, but you do have some question in mind. This form will pop up as soon as you leave the webinar, and you can submit your question there as well.
Okay, please keep giving questions through the Q&A, but we have a couple. One is, can I get a copy of the slides? And the answer is yes. We'll follow up in the next day or two and by email and give everyone a copy of the slides. The next question for Brian is, Brian, do you have any intuition on how the curved version of the mesh versus the less curved version of the mesh, those two options, how those might affect the results?
I have a little bit of intuition on it. I won't call it complete certainty, but I think particularly for that for the solar region, it's nice to have that more uniform mesh on it because it develops that gradient. I found personally that I like the smoother mesh. It tends to be a little more numerically stable. So, but I think that's nice that the user can explore those different options and look at them. But I tend to like the smoother one. It lets you see the gradients develop more clearly. Sometimes with the other one, the curvature sensitive one, you get sections where there's not a lot of resolution in certain areas, and if you have a gradient develop, you don't see that very well.
Okay, and we have another question. It says, for very complex geometries, do we find that the solver computation time becomes prohibitive? And if so, can you simplify the geometry in Cadfix to address those limitations?
Well, Tim, I think you can answer this question well. I'll just point one thing out, that yes, you can simplify it. The geometry, so basically in the end, you're only worried for the simulation part, the NASCAP simulation, you're really only worried about the mesh. And you can, there's a lot of options to work with on the mesh to get the number of elements down. So typically, if you have, say, less than 2,000 elements, it's going to simulate very quickly. If you start to get up over 3,000, it starts to slow down, but you can still do it. So it depends on how much resolution you need, but you can definitely tailor that within the EMA 3D environment to get it pretty much as coarse as you need to make sure it runs quickly.
Yeah, and like you say, Brian, I've had experience with this, taking the mechanical CAD files and combining several surfaces together to make it simpler, and then you get fewer mesh elements. And I think the computation time is like number of elements squared. So I have seen it be a problem, and I've been able to use Cadfix successfully to simplify that down. But then one of the other advantages of this platform is you can use that same geometry for your space charging, but you can turn around and use it for EMC, lightning, and other simulations. So you turn one bit of geometry, and on one platform do a lot of different analyses on it. Okay, and another question is there a maximum number of mesh cells?
I think so. I believe it's 4,000. Is that as you recall, Tim, as well?
Yeah, and I think that's a NASCAP limitation, whereas
right.
With the CAE environment, it's a general tool, so you can mesh a lot more fine than that. So it comes back to what we talked about before, is we're somewhat forced to simplify the mesh a little bit to work with NASCAP. But perhaps in the future, some of those limitations on NASCAP can be relaxed. Okay, next question is a question about being able to plot the potentials in the surrounding space or do the particle tracking. And so I think the answer to that is within Cadfix, right now we cannot do that. One would have to look at NASCAP itself. And so in that case, you would do your geometry processing and EMA 3D Cadfix, and then you'd look at your particle tracking or surrounding space in NASCAP itself. But I think both of those would be on the list of things to add in the post-processing in Cadfix in the future. And the next question, this is one for you, Brian. Can the mesh resolution be different for different regions of the model? Actually, it can be. You can, in Cadfix, change the mesh approach based on sets. So you can pick, for example, the solar cells one type of one particular tolerance, and you can change the tolerance and other features for other regions, and the boundary measure will make it all match up nicely. Okay, I think that's caught us up on all of our questions. Anything else you want to add, Brian?
No, we appreciate the questions and your attention, and we certainly welcome additional inquiries as as you maybe think of them over the next couple days. Feel free to shoot us emails and things like that.
Yeah, and like I said, I'll follow up with a copy of the slides, and feel free to reply with any questions, discussion, or feedback, good or bad, about what it does and what you would like to see it do. Thanks again for everyone's attention, and keep your eyes peeled for future webinar topics in February.